All right, let's get right into it. Today, we're talking about a piece of software called FlashAttention-4, and trust me, it's a big deal. It's basically a perfect example of how really smart code can make the most powerful AI chips on the planet even more powerful. So think about this for a second. What if these incredible AI chips, the ones that feel almost like magic, what if they had a hidden weakness? It's a fascinating thought because we tend to see them as these flawless, super powerful engines. But the reality is, even the strongest hardware has its own little quirks, its own Achilles heel that can seriously slow things down. I mean, the pace of AI is just relentless, right? It feels like every week there's a new breakthrough. But here's the catch. As these AI models get bigger and smarter, they start hitting a wall, a physical wall, the limits of the hardware they run on. And today, we're going to zero in on one of the biggest roadblocks holding AI back. So right at the heart of almost every modern AI, you'll find something called the attention mechanism. It's kind of the secret sauce in models like GPT. It's what lets an AI figure out which words in a sentence are the most important. But, and this is a big but, it has a major downside. The cost to run it explodes as the text gets longer. We're not talking a little bit slower. We're talking quadratically slower. It's a huge performance bottleneck. And that brings us to the new heavyweight champion of the hardware world, NVIDIA's Blackwell B200 GPU. I mean, this thing is an absolute beast, a monster of a chip. But, and this is where our story gets interesting, it has this quirk, this weird trade-off that actually creates a brand new set of problems. Okay, check this out, because this is the whole problem in a nutshell. Look at the tensor core speed. That's the chip's muscle, the part that does all the heavy math. It more than doubled from the previous generation. That's insane. But then you look at other crucial components, like how fast it can access its own memory, or this other little special calculator on the chip, and they didn't get faster at all. They're exactly the same. There's a term for this, asymmetric hardware scaling. And the best way to think about it is with a simple analogy. Imagine you have a chef who can suddenly chop vegetables at 100 miles an hour. Awesome, right? But if he's only got one tiny little burner on the stove, all that chopping speed is useless. He can chop all he wants, but he can't cook any faster. The stove is now the bottleneck. And that is exactly what's happening inside this new Blackwell chip. And this table here, it shows you the problem with hard numbers. These cycles are basically just ticks on a clock, how long each part of the job takes. And you can see, for the kind of big jobs Blackwell was built for, suddenly the main math unit and that special exponential unit are taking way, way longer than everything else. They've become the new speed limit for the whole system. So, what do? You can't just go in and redesign the chip. Well, the answer is you get clever. You write smarter code. And that, my friends, is where FlashAttention-4 comes in. It's a piece of software designed from the ground up, specifically to dance around these new bottlenecks on the Blackwell chip. And this quote from the paper really just nails the whole philosophy. They say they're not treating the hardware like just a big, dumb calculator. Instead, they're digging in, finding the specific bottlenecks, and then using algorithmic innovations, that is, clever code, to solve them. It's a much more surgical approach. This whole idea has a name, algorithmic co-design, and it's a really big deal in computing right now. The old way was hardware folks build a chip, then they toss it over the wall to the software folks. Co-design says, nope, that doesn't work anymore. To squeeze out every last drop of performance, you have to design the software with a deep, intimate knowledge of the hardware's strengths and its weaknesses. All right, so that's the big idea, but how did they actually pull it off? Let's get into the weeds a little bit and look at a couple of the really clever tricks they used to basically outsmart the hardware. Okay, trick number 1. Remember that slow, specialized exponential calculator that became a bottleneck? Well, FlashAttention-4 basically says, you're too slow, we're not waiting for you. Instead, it teaches the other super fast math units on the chip how to do a pretty good imitation of that calculation using a math shortcut. So now, instead of one slow worker, you have a whole team of fast workers helping out. The result? They double the speed of that specific step. Now, the first thing you're probably thinking is, wait, an imitation, an approximation, doesn't that mess up the math? And that's the genius part. It turns out their software shortcut is so incredibly accurate that by the time you round the numbers back to the format AI models use anyway, the difference is basically 0. You get all the speed with no meaningful loss in accuracy. It's brilliant. Okay, trick number 2. Now, this diagram looks pretty complicated, but the idea behind it is actually super simple. It's all about teamwork and reducing traffic. They came up with a new way for 2 different processing units on the chip to share their work. My favorite analogy for this is, imagine you have 2 chefs in a kitchen. Instead of each of them having their own giant identical recipe book they have to lug around, they just share one. It's way more efficient. They're not bumping into each other, and they're not wasting energy. It just streamlines the whole process. So we've talked about the clever ideas, the smart tricks, but the real question is, does it actually pay off? Let's look at the benchmarks. Let's see what happens when the rubber meets the road on the Blackwell B200. And wow, the results are pretty wild. This chart shows the forward pass. That's basically the AI in action, generating text or an image. And that purple bar, FlashAttention-4, is just dominating. It's not just a little bit faster, it's consistently faster than everything else, even NVIDIA's own super optimized library. It's a clean sweep. And it's the same story for the backward pass. Now, this is arguably even more important, because the backward pass is where the AI is training, where it's actually learning. Making this faster isn't just a small improvement. It means researchers can train bigger models, run more experiments, and push the entire field of AI forward at a much faster pace. And just to put a number on it, at its peak, FlashAttention-4 was a whopping 2.7 times faster than another really popular method called Triton. Let that sink in, a nearly 3x speedup, not from new hardware, but from writing smarter code. Oh, and there's another awesome side effect. The old version was written in complex C++. The new one uses a much friendlier Python-based framework. And look at the difference in compile time. That's the time a developer has to wait for their code to be ready to run. It went from 45 seconds down to 1.4 seconds. That is a huge quality of life improvement for anyone actually working with this stuff. Okay, so let's pull back from the nitty-gritty details for a second. We've seen the tricks, we've seen the impressive speedups, but what's the big picture here? Why does any of this really matter? I think there are a few really important lessons here. First, it shows that you can't just build faster hardware and expect magic to happen. The software has to be designed hand in glove with it to unlock its true power. Second, it's a powerful reminder that clever algorithms can literally work around the physical limitations of a chip. It's like finding a secret shortcut that the hardware designers didn't even know was there. Third, and this is the big one, faster tools mean faster progress for everyone in AI. And finally, by making the code easier to work with, they're opening the door for more people to innovate in this space, which is always a good thing. And all of this really leaves us with one big question for the future of AI. As the hardware gets more and more powerful, where are the biggest breakthroughs going to come from? Is it going to be from the next amazing chip, or is it going to come from a piece of clever code that nobody saw coming? Something to think about.